Dear students, today we will start uh, about some singularities, and these singularities, in the presence of these singularities, the flow will be solved with the help of complex variable technique. So first of all, we come to a type of singularity which is source, and another type of singularity which is called sink. First of all, in rough language, you may say that source is a point. You can see this point, this small point. Source is a point from where a fluid comes out radially and symmetrically. So from this point, the fluid comes out. This comes out in radial direction and it is symmetric. That means at each and every streamline, the value of the velocity is constant. And if I say that, if I want to define sink, then sink is a point towards which the fluid goes radially, or fluid sinks towards a point radially and symmetrically. Then that is called a sink. So again I am telling you what is source, what is sink. Source is a point towards which the flow is directed radially and symmetrically, and sink is a point from where a fluid is directed outward direction radially and symmetrically. So what are the properties of source and sink? First of all, this is radial. That means the fluid comes out in radial direction. This is very important point. Neither the fluid goes axially nor the fluid travels transversely. Rather, it travels only in the radial direction. Secondly, it is symmetric, which means that the streamlines which generate through a single point, at all the streamlines, the value of velocity is same. The value of velocity may be different on single streamline, but it is same at all the streamlines, at all the corresponding points. Third one is, as far as source is concerned, the flow is in outward direction, and as far as sink is concerned, the flow is in inward direction. You can very well see in these diagrams, it is the point from where fluid is coming out radially. This point is called source, and this is the point towards which the fluid is going into radially. A very beautiful example of sink is the sink which you use in your houses or in your hotels or in your bathrooms. So the next property is that the flow lines emerges from a point. एक ही point होता है, एक ही point से सारी flow lines emerge होती हैं. Area of flow gradually increases. You see, the fluid is coming out through this point. Suppose I draw a circle, then this is the area which goes on expanding and expanding. So area goes on increasing and velocity goes on decreasing. Which law is used here? Here the mass conservation law is used, that if area is increasing, then velocity is decreasing. Next, streamlines is spread out. You are seeing very well that streamlines spread out while the sink lines shrinks. Next one is velocity at all points at a given distance from the source is same. I have told you earlier that suppose these are two streamlines, and if I want to see what is the velocity at a distance r is equal to r1, then whatever be its value here, suppose it is q1, then the same value will be here at r is equal to r1 on the second streamline, and the same case will happen with all the streamlines. So if I talk about sink, same, it is radial, it is symmetrical, these are symmetrical. Inward direction, flow lines approach to a point, and area of flow gradually decreases, therefore the velocity gradually increases. Streamlines get bunched closer and velocity increases. You see, all streamlines try to come to a single point, so they converge to a point, and so velocity increases to a large extent. and velocity at all points equidistant to the sink is equal. The point is same as we discussed for the streamlines. So what important is that sources and sinks are singularities in the flow region. Why are these called the singularities? Because we have read that streamlines never meet, and if they meet or bifurcate, that is the stagnation point. So these are the extraordinary points. Source and sink, both source and sink, both are the extraordinary points where the streamlines meet. Now, these are caused due to external dynamical effects. There is no internal effect because of which the sources or sinks are produced. Rather, only external causes may, due to the external causes, the source or sink may happen. The flow around a line source or line sink is irrotational. This is another property. Now, in actual, we would try to find that what will be the complex potential function for a source or complex potential for a sink. First of all, you have seen that source and sinks are opposite to each other in one sense, that in one the fluid goes out readily and in another the flows shrinks to a point readily. Otherwise, all other properties are same for the two. So, when we derive the complex potential function for source, simultaneously we may get the complex potential function for a sink. Suppose you consider a cylinder. This is a cylinder. In this cylinder, you have three directions. You may have three directions of flow. One direction is radial direction. If your fluid is flowing in radial direction, so it is the radial direction. If it is in around the surface, then it is called circumferential direction, and in that case there will be the role of theta. And third situation may be that the fluid is going in this axial direction. So there may be fluid flowing in three directions. We assume that if we consider a cross section of the cylinder, or rather you say that if we consider the cylinder in such a way that there is only flow in a radial direction, then you can simply see that suppose it is our equation of continuity in cylindrical coordinate. No, there is some mistake in this equation. You see, this is the equation. This is the equation. Here r is missing here. Delta r u r plus delta theta u theta plus delta z u z. Here you see that there is no flow in circumferential direction. There is no flow in z direction. Rather, there is flow only in a radial direction. So you can very well understand it with this diagram, that if I talk about qz means a velocity component in axial direction. So if I consider any qz at point A and I consider qz at point B, both are same. But if I consider qr at A and qr at B at some point, that is at r is equal to r1, then both are not same. If I consider q theta at A and q theta at B, then both are again not same. So we can neglect flow in z direction. If it is the situation, we can neglect flow in z direction. And so it is called flow in diametral plane. You see this plane? This is the plane. Your flow may be in radial direction. If you imagine the cross section of a cylinder, then only you can imagine the radial direction flow. And in such type of situation, there may be transverse directional flow. So QR and Q theta may be there, which I have written here U and Q are one and the same thing. Similarly, here is the situation in which this Q theta is also not there. Only UR is there. So we get delta UR delta R is equal to 0, because in this equation of continuity you put U theta to be 0, you put UZ to be 0. So it is delta UR delta R is equal to 0, giving UR into R is equal to constant, or UR is a function of R. But again, it will give us the property that if we are at equidistant from the source or sink, then the velocity will be same. You may also see here that UR and R are inversely proportional to each other. So as your R will increase, your U will decrease. Your area will increase, your velocity will decrease, and as your area will decrease, your velocity will increase. So it is just to make you understand that how the UR is constant. Now these are the relations which we will use later. These are the relation of velocity components in terms of psi and phi. These are the velocity components. But in our article, we are concerned only with UR. We are only concerned with these two relations, that is 2A. So we come to the next part. Suppose you are considering this cross section of the cylinder. Okay. Actually, what is this? Suppose the fluid is emerging out through O. You get streamline here, 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 here. And if at the same distance R1, same distance R1, same distance R1, you try to join the all. So what type of section will you get? You will get a circle. At these all R1, the velocity is constant. Again you go to R2. On all streamlines you go to a distance R2. Because you are measuring this distance from a single point, then joining all those points, again you will get a circle. So in this way you get this type of area in which these are your streamlines. Okay. So if I take Q to be rate of flow of fluid from the source point per unit thickness of flow. Why I have taken per unit thickness? Because in this cross section you are just left with a type of plane. And what is the thickness of this plane? What is the thickness of this plane? It may be assumed to be as unit. So we consider the rate of flow of fluid from the source point per unit thickness of flow. ये सोर्स पॉइंट है, ये आपका एक प्लेन जैसा सा मिल जाएगा और ये एक सर्कुलर प्लेन है. सो हम Q की डेफिनेशन क्या लगाएंगे? इट इज़ द रेट ऑफ फ्लो, सो इट विल बी वॉल्यूम इनटू वेलोसिटी. यहाँ सर्कमफ्रेंस के थ्रू फ्लूइड बाहर आ रहा है बिकॉज यू हैव टू टेक द नॉर्मल कंपोनेंट ऑफ वेलोसिटी. जब बाहर आता है फ्लूइड तो हमेशा वो नॉर्मल वेलोसिटी से बाहर आता है, और इस सर्कमफ्रेंस की नॉर्मल वेलोसिटी क्या होगी? यू आर रेडियल, क्योंकि सर्कमफ्रेंस की नॉर्मल डायरेक्शन क्या होती है? रेडियल डायरेक्शन होती है. तो दिस विल बी यू आर. नाउ वॉल्यूम, this is the circumference 2 pi r multiplied by the unit thickness. So it is 2 pi r into 1 into ur. This will be your rate of flow of fluid from the source. So what will be qr? Ur, solve it for ur. Ur will be q upon 2 pi r. Suppose we take r to be 1. r को हमने 1 ले लिया तो ur कितना आ गया? k upon r. And this k upon r is assumed to be as this q upon 2 pi. ur में जब हम r को 1 रखेंगे we will get ur is equal to q upon 2 pi, and this q upon 2 pi is assumed as k. So what is ur? ur is equal to k upon r. Now suppose I assume that radius is also unit, तो ur किसके बराबर हो जाएगा? k के बराबर. This k is called source strength, which is what? Which is the velocity of flow at unit radius. Ur is what? Ur is, if I say that ur to be k, then what is k? K is the strength of the source, and k is equal to velocity of the flow at unit radius. Okay. So in this way we get UR. UR is K upon R. Now as I told you that UR can be written in terms of stream function. So value of UR in stream function in terms of polar coordinates is 1 upon R delta psi delta theta. You put here K upon R is equal to 1 upon R delta psi delta theta. Solve it, get K is equal to delta psi delta theta. Integrate, you get psi as K theta plus some constant of integration, which may be a function of phi because phi is assumed to be constant here. Oh, sorry, this should be R. This is not phi, this is R. This is R. Now, theta is equal to, at theta is equal to theta 1. Suppose I put theta is equal to theta 1. You will get some value of psi. Let I give it name psi 1. This is psi 1. So, at the location theta is equal to theta 1, you get a streamline, and that on that streamline your psi 1 is K theta 1 plus constant, or rather K theta 1. You can see here, this is the horizontal line, initial line. From this line we get a line theta is equal to theta 1. This is theta 1 and I get this line. At this line the value of psi is psi 1, which is psi 1 is equal to K theta 1. Likewise, if I put theta is equal to theta 2, I get psi is equal to psi 2. So, you measure K is equal to theta 2 and you get another streamline. And on this line, the value of the stream function is this psi 2. Likewise, you will get so many streamlines for different values of theta, and at each and every streamline, the stream function will have corresponding value, but stream function separately will be constant on each straight line, or rather you can say on each streamline. So now we get different streamlines corresponding to different values of theta. Now we again come to UR because we can find the value of psi, but for complex variable technique we also need the value of phi. So we put UR is equal to delta phi delta R. UR की दो values हो सकती हैं in terms of psi, in terms of phi. So in terms of phi it is delta phi delta R. Put the value of UR, solve it for phi, it is K log R. Can you recognize it? If I put psi is equal to constant, I put K log R is equal to constant, and simply I'll get R is equal to A, that means the equation of a circle. You may solve it very easily to see that 7 will represent you the equation of a circle. So potential lines are derived for different R. And what are these potential lines? These are circles. You may see in this diagram. This is the line corresponding to streamline, or this is the value of theta which corresponds to a streamline, and this is the line which is corresponding to a potential line. Okay. As you get different value of R, suppose here we get R is equal to A1, we get one circle. If I get R is equal to A2, we get another circle. So in this way, these are the potential lines and these are the streamlines, and we may easily see that these are perpendicular to each other. So in this way, we got our psi, we got our phi, and so we can say that for different values of R, we get different phi 1. For R is equal to R2, we get phi 2, and this is the value of phi 2 and all this. Practically it has been seen that there is no effect of these constants C1, C2 and all that, so we can assume these to be 0. Similarly, what we do for the sink, we may write with negative symbol. K is strength, you remember it. So we write psi is equal to minus K theta and phi is equal to minus K log R. In source, we have derived psi is equal to K theta. In sink, psi will be minus K theta. So there is the difference of only symbol. But you should keep in mind that in some books, both are having the opposite symbol. That is, these values are found for source, and with positive the values are found for sink. So again, this is only the question of the consideration of phi. If you consider phi to be from high potential to low potential or low potential to high potential. This is the difference of that. So it will not affect your description of flow. Now we again write what is W. W will be phi plus I psi. Put the value of phi, put the value of psi. Change this k theta in terms of log. Combine the two. This will be k log r e raised to the power I theta. This is r. This is e raised to the power I theta. The solving. In place of r e raised to the power I theta, I can put z. So it is k log z minus z naught. Where what is z naught? It is 0. So what is the result? That if a source is placed at origin, this is origin, and its strength is k, this is the strength, then W, this is W, is equal to k log z, where phi is equal to k log r and psi is equal to k theta. Or what is r and what is theta? R is modulus of z minus z naught and theta is argument of z minus z naught. So now this is our answer, that it is the complex potential if there is a source placed at origin and k is its strength. Similarly, if there are there is source which is not placed at origin, rather it is placed at some point. Suppose it is placed at z naught. You see here, note, if source is placed at some point z is equal to z naught, then what will be the value of this complex potential? W will be minus k or plus k log z minus z naught. If a source is placed at some point z naught, then we may write like this. Putting phi is equal to constant, you may get the equation of streamlines. Putting psi is equal to constant, putting phi is equal to constant, we may get the equation of potential lines, and for psi is equal to constant, we may get the streamline. So in this way, we can describe our streamlines here. You can see a very simple example here. Suppose this type of W is given. W is equal to log z minus a square upon z. Actually, you may be given two types of examples, two types of questions. In one question, W is given and you have to recognize that what type of sources, sinks or doublets are involved in the question. And there may be another type of examples where they will give you that which source, which sink is there in the flow region, and they will ask you to frame the complex potential. So there may be two types of questions. This is only first type of question in which W is given. W is log z minus a square upon z. And they are asking you about what is the arrangement of source and sink here. So it is very simple to solve it. You write it in this way. Take z LCM, write in this way. Z square minus a square को भी खोल दीजिए. This may be opened as z minus a into z plus a. Open like this. Now you can very well understand, you can very well recognize that here it is 1 into log z minus a plus 1 into log z plus a minus 1 into log z. And we know that if I assume the value of phi, you have to mention here the value of phi, that what type of relation between u and phi are you assuming. So here I have written sink, you may also write source, but in that case you have to give here what relation is you assuming, what relation are you assuming. So here you will see that there is a sink of strength 1 because 1 into, there it was k into, so k was the strength, here it is 1 into, तो यहाँ 1 क्या हो जाएगी, स्ट्रेंथ हो जाएगी. प्लस वाले को यदि आप सिंक के लिए ले रहे हो तो आप कहोगे 1 स्ट्रेंथ की सिंक है जो z इज इक्वल टू ए लिखा है z माइनस ए, तो कौन से पॉइंट पर प्लेस्ड है, A0 पॉइंट पर. एक और सिंक है यूनिट स्ट्रेंथ की जो यहाँ माइनस ए देगा, माइनस A0 पर प्लेस्ड है, और माइनस सिंबल की वजह से कहोगे एक सोर्स है जो कि z को कैसे लिख सकते हो, z माइनस 0, तो वो किस पॉइंट पर है, 0 पॉइंट पर है. 0 मतलब 0 पॉइंट पर है. So what is the arrangement of source and sink? There are two sinks of unit strength placed at A0 and minus A0 and a source placed at origin. Or you may write in another way you should give both. In other way, you can say that there are two sources of unit strength placed at A0 and minus A0, and a sink of unit strength placed at 0. Is it clear? Now we come to how will we find the streamlines and potential lines. In place of this W, you write W plus phi plus I psi. In place of this Z, you write X plus IY. Z की जगह लिखो X plus IY. Real parts को separate कर लो, imaginary को separate कर लो. From here, this is a relation. If you have log alpha plus I beta, then you may write real and imaginary part separately. Half log alpha square plus beta square plus I tan inverse beta upon alpha. So using this relation, you can open these three logs. So in this log, you will get one real part in this log, in all the three you will get real parts. I have separated all the three parts and get this phi. Phi is equal to, I'll get this expression. Solving for psi, psi will be this much. Solve it for tan inverse. इसको solve कर लिया पूरा. Now suppose I have to give the value of streamlines. The streamlines will be given by psi is equal to constant. So they take that constant to be 0. So this will be equal to 0. tan इधर चला जाएगा. तो this will be equal to 0. अगर मैं इसे 0 रखूँ इसको, तो मेरे पास क्या आएगा 0 रखने पर? एक तो आएगा y इज इक्वल टू 0, एक आएगा एक्स स्क्वायर प्लस वाई स्क्वायर प्लस ए स्क्वायर इज इक्वल टू 0. यहाँ से हो जाएगा एक्स स्क्वायर प्लस वाई स्क्वायर इज इक्वल टू माइनस ए स्क्वायर. सो इज इट पॉसिबल? इट इज़ नॉट पॉसिबल. तो विच लाइन्स आई एम गेटिंग एज स्ट्रीम लाइन्स? ओनली y इज इक्वल टू 0. y इज इक्वल टू 0 क्या रिप्रेजेंट करता है? एक्स एक्सिस को रिप्रेजेंट करता है. तो यहाँ से क्या आया कि जो स्ट्रीम लाइन होंगी वो पैरेलल टू एक्स एक्सिस होंगी. ठीक है. अब आप देखो लोकेशन क्या आई थी. लोकेशन आई थी आपकी A0 पर. ये 0 0 है, ये A0 है और ये माइनस A0 है. तो इस A0 पर यदि मैं सिंक मानूँ तो मुझे इस तरह बनानी चाहिए लाइन. ऐसे बनानी चाहिए सिंक की तरफ आती हुई. सिंक की तरफ आ रही है और यहाँ पर ये एरोज बने हुए हैं. अगर मैं सोर्स मानूँ तो मुझे इसे बाहर की तरफ एरो लगा देनी चाहिए. सो आई शुड गिव इन बोथ वे. ये आपकी स्ट्रीम लाइन बता रही है यहाँ से. और दूसरा हमने कहा कि एक सिंक भी होगा. दूसरा हमने क्या कहा कि एक सिंक भी होगा. यदि इस कांस्टेंट को मैं 0 की जगह इन्फिनिटी ले लूँ, इन्फिनिटी लेते ये नीचे वाला 0 हो जाएगा. डिनोमिनेटर 0 होते मुझे क्या मिलेगा? x इज इक्वल टू 0 मिलेगा और एक्स स्क्वायर प्लस वाई स्क्वायर इज इक्वल टू ए स्क्वायर मिलेगा. x इज इक्वल टू 0 का क्या मतलब है कि y एक्सिस मिलेगा और एक्स स्क्वायर प्लस वाई स्क्वायर इज इक्वल टू ए स्क्वायर का क्या मतलब है कि सर्कल्स मिलेंगे. और सर्किल का रेडियस क्या होगा? a होगा. तो आप a को रेडियस मानते हुए, इधर a को रेडियस मानते हुए ऐसे करके एक सर्किल ड्रॉ कर दीजिए. अब हमने एक तो सर्किल ड्रॉ कर दिया, एक हमारी ये बाउंड्री आ गई और एक हमारी ये बाउंड्री आ गई. अब हमें इस तरह से बनाना है जैसा हमने सोचा है, जैसा हमने विजुलाइज किया है, ऑब्जर्व किया है. हमने यहाँ से ये ऑब्जर्व किया है कि हमारे यहाँ अगर सिंक है, यहाँ अगर सिंक है और यहाँ अगर सोर्स है, तो हम कैसे बनाएंगे? हम एक लाइन निकालेंगे यहाँ से, जो यहाँ से निकली और यहाँ अंदर चली जाएगी. यहाँ से निकलेगी, यहाँ अंदर चली जाएगी. यहाँ से निकल रही है, अगर मैं इसे सोर्स कह रही हूँ तो मैं एरो ऐसे बनाऊंगी, और यदि इसे सिंक कह रही हूँ तो ऑटोमेटिकली ये अंदर ही जा रहा है. पर जब मैं इधर से लाइन बनाऊंगी, ये वाली लाइन बनाऊंगी, तो यदि मैंने सिंक का है तो मैं एरो ऐसे बनाऊंगी, यदि मैंने इसे सोर्स का है तो मैं ऐसे एरो का डायरेक्शन बाहर की तरफ कर दूंगी. तो पहले हम इन्हीं को ड्रॉ कर लेते हैं. इनको ड्रॉ करने के बाद ये एक सर्किल भी, एक सर्कुलर बाउंड्री भी हमें मिली है. यहाँ पर मिली है ना सर्कुलर बाउंड्री. यदि इस सर्कुलर बाउंड्री के लिए हम क्या करेंगे? यदि हमारा ये सिंक है तो, और ये लाइन है, इसके अराउंड ये ऐसे करके एक बनेगा पैरेलली. ठीक. यदि ये मैंने सिंक माना है ना, तो ये पैरेलली फिर ऐसे जाएगा, ये यहाँ से भी ऐसे चला जाएगा, लेकिन एरो अंदर की तरफ बनेगा. ऐसी एरो यहाँ पर अंदर की तरफ, क्योंकि ये हम सिंक कह रहे हैं. ऐसे ही नीचे से आएगा तो एरो अंदर की तरफ बनेगा. और अगर आपने सोर्स और सिंक को अलग तरह ऑब्जर्व किया है सिंबल की वजह से, तो आप ये सारे एरो जितने भी बने हुए हैं इनको उल्टा बना देंगे. So this is all about the complex potential of a source together with one example. Now you go through your book, you will get so many examples regarding source and sink. You solve all these examples and discuss if you have any type of difficulty over there. Thank you so much.